We will now use the theoretical results we obtained in the last class to solve problems. So to begin with, let's review the important formulae we derived in the last class. What are the formulae we derived in the last class? The displacement of a simple harmonic motion. Do you remember that equation? The displacement y as a function of time is a sine omega t plus delta. The velocity of a simple harmonic motion is the derivative of the displacement is given by a omega cos omega t plus delta. Acceleration is the derivative of the velocity given by acceleration is negative a omega squared sine omega t plus delta. And also we rewrote it as a sine omega t plus delta is y. So acceleration equal to negative omega squared y. Now this is the typical equation for a simple harmonic motion. Acceleration is proportional to displacement and it takes place in the opposite direction. What is the maximum value of y? Maximum value of y is a, the amplitude. If you look here, you can see, tell me, what is the maximum value of the sine quantity? If you know your sine values, sine has the maximum value of 1. Sine of pi by 2 is 1. You see, all other sine values will be less than 1. So maximum value of the sine quantity is 1. Therefore, maximum value of the displacement is the amplitude A. Well, even otherwise, amplitude is the definition of amplitude is the maximum displacement. In that case, can you look at this equation for velocity and tell me what is the maximum value of the velocity? We derived an equation for it in the last class, but looking at this, you can get the maximum velocity right away. How? If you know that the value of a cosine function, the maximum value of a cosine function is 1. Is that right? Yes. So the maximum value of this quantity is 1. Therefore, the maximum value of the velocity is a omega. Alright? In that case, tell me what is the maximum value of the acceleration? The maximum value of the acceleration occurs when the sine omega t plus delta becomes 1. And because we are looking for the maximum value, we will remove that negative and say maximum acceleration is a omega squared. Alright. Omega equal to square root of k over m. Do you recall that equation? And omega also is related to the period. What's the relation between omega and the period? Omega equal to 2 pi over t, the period. It is also related to the frequency as 2 pi times f. Alright, all these formulae must be familiar to you. And frequency and the period are, one is the reciprocal of the other. Potential energy of a stretched spring. What is the equation for the potential energy of a stretched spring? U equal to 1/2 kx squared, where x is the amount of stretch. If you use y as the amount of stretch, it will be 1/2 ky squared. Kinetic energy of an oscillating mass, of course, is k equal to 1/2 mv squared. What is the total energy of an oscillating object? The total energy is made up of the potential energy and the kinetic energy, and we know that the total energy remains a constant and is equal to 1/2 Ka squared. F equal to negative kx or negative ky. The restoring force of a spring is proportional to the displacement and takes place in the opposite direction. We talked about that too. The maximum kinetic energy occurs at the equilibrium position, right? At the equilibrium position, the potential energy is 0, the kinetic energy is maximum. So K max equal to 1/2 mv max squared. That is equal to 1/2 Ka squared. You see, that's the total energy. Now, solving that gives you the same equation. We have actually seen this equation before. Vmax equal to omega A, and omega is square root of K over m. So, all these equations will be useful as we go on to solve problems. Alright, let's do example 1. A 2 kilogram object attached to a horizontal spring. So this time the spring oscillates horizontally. The spring constant K equal to 5 Newton per meter. The spring is stretched 10 centimeter from the equilibrium position and released. Now tell me, if the spring is stretched 10 centimeter from the equilibrium position and released, that information, that 10 centimeter is the maximum displacement, because the displacement cannot be greater than that. If I stretch a spring to 10 centimeter and release it, that will be the displacement from the equilibrium position. That is a measure of the maximum displacement. Alright, we need to find the period, the frequency, the amplitude of the motion. If you understood what I just explained, you know the amplitude of the motion. Amplitude is the maximum displacement. And isn't this the maximum displacement? So you know the answer to C already. What is the maximum speed? What is the maximum acceleration? You see, you simply use the formulae. And when does the object first reach the equilibrium position? What is the acceleration at this time? This also you can answer quite rapidly, quite quickly. What is the acceleration of the object at the equilibrium position? At the equilibrium position, the acceleration is 0. Acceleration is maximum at the two extremes. And at the equilibrium position, there is no net force. Alright, let's do each of these. Here is the situation. This is the equilibrium position. And the object is pulled to the right a distance of 10 centimeter. Mass of the object is 2 kilogram. The spring constant is K equal to 5 kilonewton per meter, 5,000 Newton per meter. Amplitude is the maximum displacement, 0.1 meter. Alright. Period T, what is the equation for the period of oscillation of a spring like this? Do you recall that equation for the period? I don't think I put that equation earlier on. Period T of oscillation is 2 pi square root of MOK. Well, you add this equation along with the other equations. This is the equation for the period of oscillation, whether it is horizontal or vertical. Well, you know the value of M, you know the value of K, so substitute those values. That gives you the period is 0.126 seconds. In other words, the time taken for one complete oscillation is 0.126 seconds. Alright, let's go and do the next one, the frequency. Alright, if you know the period, what is the frequency? Frequency is 1 over the period. So frequency is 1 over the period. Our period is 0.126 seconds. Therefore, it is 1 over 0.126. That is 7.94 Hertz. Alright, we did A, B, C. What is the answer for C? It's right there. The amplitude is the maximum displacement since the spring is stretched to 10 centimeters from the equilibrium position. This is the maximum amplitude. You see? That is the maximum amplitude, maximum displacement. Therefore, that is the amplitude. What is the next one? What is the maximum speed? Alright, what is the equation for the maximum speed? V max. In order to find the maximum speed, we need to obtain omega. And what is omega equal to? Omega equal to 2 pi f. We just calculated the frequency. So use that value. We got 2 pi times 7.94. That is 49.9 Hertz is omega. And what is the equation for maximum speed? Vmax equal to A omega. See, look at this. Once you know the equation, problem solving becomes very easy. Vmax is A omega. A is 0.1 meter. Omega is 49.9 Hertz. And therefore, that is 5 meter per second. That is the maximum velocity. Tell me, when does this mass have this velocity, this 5 meter per second? At what position? The maximum velocity occurs when it reaches the equilibrium position. So this is the velocity at the equilibrium position. Alright, next what do we need? What is the maximum acceleration? What is the equation for maximum acceleration? A equal to, well, acceleration is negative omega squared y. And this becomes maximum when y equal to A. Is that right? When y has the maximum velocity. The acceleration becomes maximum when y equal to A. And since we are looking for the maximum value, we will not use the negative sign. So A max equal to omega squared A. And we know the value of omega. We know the value of A. Therefore, maximum acceleration is 249 meter per second squared. Now, well, we found the maximum acceleration. Next, when does the object reach the equilibrium position? When does? After what time? Do you remember we obtained the period of oscillation? We have calculated the period of oscillation. Now, look what happens. If you leave the object here, it has to come back to the equilibrium position, go to the left extreme, come back to the equilibrium position, and be on the right extreme. That is one full oscillation. That means the time taken for this object to come to the equilibrium position is a quarter of a period. Do you understand that? This is the right extreme. Coming to the equilibrium position is 1/4 of the oscillation. It comes to the equilibrium, goes to the left extreme, comes back to the equilibrium, and back on the right extreme. That is one full oscillation. So the time taken to reach the equilibrium position is a quarter of a period. Since the object is released from the extreme right, it reaches the equilibrium position in 1/4 of a period. And you know we calculated the period as 0.126 seconds. Therefore, the time taken by this object to reach the equilibrium position is a quarter of 0.126. That is 0.032 seconds. what is the acceleration at this time? What is the acceleration when the object reaches the equilibrium position? We talked about it. At the equilibrium position, there is no force on the object. There is no acceleration at the equilibrium position. Alright, let's do another problem. A 5 kilogram object oscillates on a horizontal spring. Here again you have a horizontal spring with an amplitude of 4 centimeters. Always pick out the given values. Its maximum acceleration is 24 meters per second squared. Maximum acceleration is given to you. Find the force constant K of the spring, the frequency and the period of motion. Okay, let's start picking the data. Alright, the mass of the object is 5 kilogram. M equal to 5 kilogram. Amplitude is given to be 0.04 meter. And now, what else do we have? The maximum acceleration is given to us. Do you know the equation for maximum acceleration? Maximum acceleration is A omega squared. There you are. A max is given to us. Now, once you know the maximum acceleration, you can use this equation A omega squared and find the value of omega. You see, once you find the value of omega, you can find frequency. Why? Because omega equal to 2 pi f. And once you have the frequency, you can find the period and so on. Alright? A max equal to omega squared A, and you know the value of A max, 24. And well, you can see here I have used, instead of omega squared, in place of omega squared I wrote K over M. Isn't the same thing? Omega is square root of K over M. Omega squared is K over M. Why have I done that rather than finding the value of omega? Because in our part A, we are looking for the value of K. That's why I use that. So A max equal to K over MA. And this quantity must be equal to 24 meters per second. Let's solve for K. Now, A max equal to K over MA. What is K equal to? Look at the way I'm going to solve it. K is A max times M divided by A. A max times M divided by A. And A max is 24, mass is 5 kilogram, and the amplitude is 0.04 meter. And that gives you the value of K as 3000 Newton per meter. Alright? Now, in part B, we need to find the frequency. So we go back here. Omega squared is K over M. And we just calculate the value of K. You know the value of M. And therefore, omega squared is 600 per second squared, square of hertz. And therefore, what is omega? Omega is square root of that, which is 24.5 per second, which is the same as hertz. Once you know omega, can you find the frequency? Well, omega equal to 2 pi f. Therefore, f equal to omega divided by 2 pi. Frequency equal to omega divided by 2 pi. And omega is 24.5 hertz divided by 2 pi. And that is 3.9 hertz is the frequency. If you know the frequency, can you find the period? Period is 1 over the frequency. T equal to 1 over the frequency, which is 1 over 3.9 hertz, and that is 0.256 seconds. Alright? These are very basic problems. And as long as you know all the basic formulae, you can work them out. Another one, example 3. A particle in simple harmonic motion has the displacement x equal to 0.4 sine 3t plus pi by 4, where x is in meters and t is in seconds. Where is the particle at t equal to 0? At t equal to 0.5. Find the frequency f and the period t of motion. Well, this is the position function, is that right? The x equal to 0.4 sine 3t plus pi by 4 is the position function of the oscillating object. In other words, it gives you the position of the oscillating object at any given time t. So, if you want to find the position of the object, where is the particle? What is its position? Well, all you need to do is set t equal to 0 in the equation and solve for x. Let's pick out the data here. The displacement of a simple harmonic motion is x of t equal to a sine omega t plus delta. Now, we used y of t in our theoretical derivation. That's because we used vertical oscillation. For horizontal oscillation, the displacement is x. X of t is a sine omega t plus delta. Now, look at the given equation. X equal to 0.4. So, what is the value of a, the amplitude? It's 0.4. 3t, what does that 3 stand for? 3 is your omega. The value of omega is 3 plus pi by 4. What does pi by 4 represent? Delta, the phase angle. So when you are given an equation, you should be able to pick information from it. So amplitude A equal to 0.4 meter, omega equal to 3 hertz, and delta equal to pi by 4. These are the information that is contained in the given position function. Alright? The position of the object at t equal to 0. To find the position of the object at t equal to 0, simply put that t to be equal to 0. So x of 0 is 0.4 sine, look at this, 0.4 sine, 3t is 0, so the quantity inside becomes pi by 4, sine of pi by 4. Anybody tell me the value of sine pi by 4? I'm sure most of you know it. Sine of pi by 4 is root 2 over 2. But you can put this in your calculator and obtain the value. I got this as 0.28 meter. So at t equal to 0, the oscillating object is at 0.28 meter. Alright? Sometimes to the right of the equilibrium position. Alright. Where is the object at t equal to 0.5 seconds? The position of the particle at t equal to 0.5, what we need to do is set this t equal to 0.5. So that will be x of 0.5 equal to 0.4 sine 3 times 0.5 is 1.5 plus pi by 4. Again, put that in your calculator. It'll give you 0.302 meter. Alright, we have done A and B. Find the frequency F. Where are you going to get the frequency from? Well, the frequency is contained in omega. Omega equal to 2 pi f. So the angular frequency omega is given by omega equal to 2 pi f. Therefore, f equal to omega divided by 2 pi. Omega is 3 hertz. divided by 2 pi, that is 0.48 Hertz is the frequency. And of course, if you know the frequency, you can now find the period. Period is the reciprocal of the frequency. T equal to 1 over f, that is 1 over 0.48 per second. That is 2.1 second. Okay, let's go and do another problem. Example 4. An object of mass m is supported by a vertical spring of force constant 1800 Newton per meter. When pulled down 2.5 centimeter from equilibrium and released, the object oscillates at 5.5 Hertz. That's the frequency. Find m, the mass of the oscillating object. Find the distance the spring is stretched from its natural length when the object is in equilibrium. Now what you have been told is an object of mass m, this is the object of mass m, is supported by a vertical spring of force constant. The K value of the spring is 1800 Newton per meter. And what is done when pulled down 2.5 centimeter from the equilibrium position? Now, this is the equilibrium position, right? If you pull it down 2.5 centimeter from the equilibrium position and release, it oscillates with a frequency of 5.5 Hertz. What are we need to find? Find the mass, find the distance the spring is stretched from this natural length. Look at this. This is the natural length. What is the distance the spring is stretched when the mass is hanging from it? We need to find that distance, right? Well, actually that distance will be the amplitude, is that right? Because once the spring, well, alright, we will talk about that as we go on. Okay, this is the situation, this is the equilibrium position, that means the natural length will be somewhere there. This is the lower extreme, and the object is pulled down 2.5 centimeter, means the amplitude of vibration will be 0.025. Do you understand that? You see, the distance you pull down, this is the equilibrium position. When you pull down the mass, the distance at 2.5, that is going to be the maximum displacement. This is displacement 0. Displacement now is 2.5 centimeter. That is the maximum displacement or the amplitude of oscillation. So we got K equal to 1800 Newton per meter. Amplitude is 0.025 meter. Always pick the data for doing the problem. The frequency is 5.5 Hertz. Alright, to find m, we first find omega. Because, you know, omega equal to square root of K over m. So, if you want to find m, we better find omega. Because you know the value of K. Alright, omega equal to 2 pi f. You are given the frequency. So, we obtain the value of omega from this equation. Omega equal to 2 pi f. 2 pi times 5.5 Hertz. And what is that equal to? 34.6 Hertz. And now we write omega squared equal to K over m. Omega equal to square root of K over m. Omega squared is K over m. Now we are looking for m. So solve for m. What is m equal to? M equal to K over omega squared. K is 1800 Newton per meter. Omega squared is 34.6 square. Omega is 34.6 and square it. And that gives me m equal to 1.5 kilogram. So we found the mass m. Okay, let's now go to B part. Find the distance the spring is stretched from its natural length when the object is in equilibrium. That's simple, isn't it? Because the spring is stretched by a force. What is the force stretching the spring? The force stretching the spring is the weight of this mass. That means we will be able to say F, the stretching force, equal to K times the displacement. Is that right? I think so. The force stretching the spring is F equal to mg, the weight of this object. That will be, the mass is 1.5 kilogram times g, that gives you 14.7 Newton. If y is the distance the spring is stretched from the natural length, then this force must be equal to K times that y. F equal to Ky, and therefore y equal to F over K. And F is 14.7 Newton, K is 1800 Newton per meter, and that is 0.0082 meter. And that is the distance the spring will be stretched when the mass is hanging from it. Alright? Example 5. A 3 kilogram object oscillates on a spring with an amplitude of 8 centimeter. Its maximum acceleration is 3.5 meter per second squared. Find the total energy. Anybody remembers the equation for the total energy? Total energy of an oscillating system is 1/2 Ka squared. Alright, let's see what we have. We have a vertical spring oscillating and a 3 kilogram mass is hung from the spring. The amplitude of oscillation is 0.08 meter. It is given 8 centimeter. Remember, always pick the data in the proper unit. Do not use centimeter, meter, kilogram, Newton, and so on. Amplitude is 0.08 meter. Mass of the object is 3 kilogram. And the maximum acceleration is given to be 3.5 meter per second squared. Tell me, what is the equation for the maximum acceleration? Maximum acceleration is A omega squared. Now, what is the total energy? Total energy E is 1/2 Ka squared. We need to find that total energy. Now, what do we know from here? We know the value of A. We need to find the value of K so that we can find the total energy. Now, what is in here that will help us obtain the value of K? Anybody tell me? What will lead us to find the value of K? Well, we can start looking at this. You know the maximum acceleration. Maximum acceleration is, well, this happened by mistake. The maximum acceleration is A omega squared, where A is the amplitude. Now that means you can find your omega from there. Why do you need to find omega? Because the value of K can be found if you know the value of omega. Omega squared is K over M, or omega equal to square root of K over M. So first we find omega, the angular frequency, from this given data. A max equal to A omega squared. Therefore, omega squared equal to A max divided by A. That will be A max is 3.5 meter per second squared, amplitude is 0.08 meter, that is 43.75 per second squared. And therefore, omega squared, you know, is K over M. There you are. But omega squared equal to K over M. So we bring this value of omega squared here. The value of M is known to us, and so we can find the value of K. K over M equal to omega squared, that is 43.75. That means K equal to 43.75 times M, and M is 3 kilogram. That gives you K equal to 131.25 Newton per meter. Well, you have now obtained the value of K. Now look at the path we took to find that value of K. You must be able to do this on your own. And once you have the value of K, we say the total energy is 1/2 Ka squared. And we know the value of A. We now obtain the value of K, and that will be 1/2 times K is 131.25 times A squared 0.08 squared. That is 0.42 joules is the total energy of that oscillation. Okay, I hope now you can solve any such problems. Let's look at another example. A spring of force constant K equal to 250 Newton per meter is suspended from a rigid support. An object of mass 1 kilogram is attached to the unstretched spring and the object is released from rest. How far below the starting point is the equilibrium position of the object? Now, you must understand, if I now put this object and release it, will it stop at the equilibrium position? No, watch this. Look at that. It went all the way down to the lower extreme. You see that? And then it starts oscillating. Okay, so we have what other things we know. This is the starting position. And when you allow it to fall, it falls all the way to the lower extreme and then begins to oscillate. We need to find how far below the starting point is the equilibrium position. Alright, let's see. There are many parts for this. We will do one at a time. What other things we know? We know the K value of the spring. K is 250 Newton per meter. We know the mass of the object is 1 kilogram. When the attached mass is released, the force stretching the spring. What is the force stretching the spring? Is the weight of this object. F equal to mg. And that will be 1 kilogram. You see, mass is 1 kilogram times 9.8. So that force is 9.8 Newton. And this force stretches the spring by a distance y to the equilibrium position, such that F equal to negative ky. We don't need the negative sign here to find the value of y. The negative sign simply tells you that the force is opposite to the direction of displacement. We don't need that negative sign there. So y is the distance of the equilibrium position below the starting. This is the distance y, the distance of the equilibrium from the starting position. Therefore, y equal to F divided by negative k. Well, even if you use the negative sign will indicate that the distance is measured downward. So that y equal to negative 9.8 divided by 250, that is 0.039 meter. So this distance is 0.039 meter. Alright, what is the next problem we need to, how far below? Alright, so the equilibrium position is 0.039 meter below the starting position. The object now will oscillate with an amplitude, is that right? The amplitude of oscillation will be 0.039 meter. That means, what will be the distance it is now going to go down? That will be again 0.039 meter. Alright, now look at the B part. How far does the object move before it starts up again? In other words, what is the distance it will go down? What is the distance? Tell me, what will be its distance from the starting position to the lower extreme? If this distance is 0.039 meter, and this is going to be the amplitude of oscillation, then this distance also will be 0.039 meter. So B part can simply be answered just like that. Will be 0.039 meter plus 0.039 meter. That will be 0.078 meter below the starting position. But I'm going to do this part of the problem in another way to show you how energy considerations can be used to solve a similar problem. From the equilibrium position, the mass will move down to the lower extreme, a distance equal to the amplitude. The object will now move down 0.039 meter from the equilibrium position before it moves up again. Alright, what to see? What is the period of oscillation? Well, by the way, I haven't actually done that using energy conditions. You will be good enough in answering that B part, saying that the distance from the starting position to the equilibrium will be the same as the distance from the equilibrium to the lower extreme. So that the total distance from the starting position to the lower extreme will be 0.078 meter. Alright, next part C. What is the period of oscillation? What is the period of oscillation of the object? Now, what is the equation for the period of oscillation of a loaded spring? We used that in our first problem. Period is 2 pi square root of m over k. Alright, we know the value of k, we know the value of m, therefore it is a simple matter of substituting. That will be 2 pi times square root of 1 over 250. That is 0.4 seconds. What is the D part? What is the speed of the object when it reaches the equilibrium position? Well, when it reaches the equilibrium position, its speed will be the maximum. That means all the energy will be kinetic. In other words, all the energy is kinetic, means the total energy at the equilibrium position will be 1/2 mv max squared. And that total energy equal to 1/2 ka squared. Alright, we want to find the value of V max, the velocity at the equilibrium position. Solve for V max. We have done that again in the last class. V max is square root ka squared over m. Alright, we know k, we know a, we know m. Substitute those values and that will give you the maximum velocity is 0.62 meter per second. The maximum velocity occurs at the equilibrium position. Okay. Another one. The period of an oscillating particle is 8 seconds. At t equal to 0, the particle is at x equal to a equal to 10 centimeter. Sketch x as a function of time. Draw a graph of the position function. Now, find the distance traveled in the first second, in the second second, in the third second, and the fourth second after t equal to 0. Alright, let's pick up our data. The period of oscillation is 8 seconds. It takes full 8 seconds to complete one oscillation. Amplitude is 0.1 meter. Now, where is the starting position? Is the object starting at the equilibrium position? No. At t equal to 0, the particle is at x equal to a. It starts at the right extreme. That means, what is the phase angle at that time? Now remember, I explained the phase angle to you by taking the vertical motion. From the equilibrium, if you go to the upper extreme, the phase angle is pi by 2. Back to the equilibrium, phase angle is pi. Lower extreme, the phase angle is 3 pi by 2. Back to the equilibrium, the phase angle is 2 pi. That means one complete oscillation. Alright, the same thing occurs when you are having horizontal oscillation. Right? If the object starts on the right, that means from the equilibrium it has actually come to the right. The phase angle is pi by 2. You see that? So at t equal to 0, the object is at x equal to a here, means the phase angle is pi by 2. At t equal to 0, the particle is at the right extreme. This means that the phase angle delta equal to pi by 2. And therefore, can you write the equation? What is the equation of the position function? What is the position function? Assuming that the particle is moving horizontally, the position function x will be given by, alright, I would like you to write that down. X equal to a sine omega t plus delta. X equal to a sine omega t plus delta. Alright, you know the value of a. Do you know the value of omega? Well, omega can be found from the period. If you know the period, you know the value of omega. And you know the value of delta. Delta is pi by 2. Alright? Omega equal to 2 pi divided by the period. And that is 2 pi divided by 8. And that is pi by 4. So omega is pi by 4. Delta is pi by 2. Look at the equation of the position function. The position function is now x of t. Remember, x is a function of time. X of t is a 0.1 sine omega t. Pi by 4t plus delta, that is pi by 2. You can now draw a graph of this on your calculator. Now, you know that sine of omega t plus pi by 2 is the same as cos of omega t. I showed you that in the last class. So your position function now is x equal to 0.1 cos pi by 4 t. Now this is the graph of that function. I obtained this on my calculator. You can draw it on the calculator. Alright? Take the scale, x scale from 0 to 4 pi, and the y scale, you can see the maximum value of this x will be 0.1. Therefore, you must take the scale, say x scale from negative 0.12 to positive 0.12, and you can see the graph will be traced out. Alright, so x equal to 0.1 cos pi by 4t is the position function. Now what do we need to do now? We need to find the distance traveled in the first second. Now, how do you know, how do you calculate the distance traveled in the first second? Well, we need to find the position when t equal to 1. The position at the end of the first second is x of 1 equal to 0.1 cos pi by 4, because pi by 4 t is 1. So at the end of 1 second, where is the oscillating object? The oscillating object is here, x equal to 0.071 meter. Now, you can see the distance traveled in the first second. What is the distance traveled in the first second? At t equal to 0, the object is at x0. At t equal to 1, it is at x1. Therefore, the distance traveled in the first second is x0 minus x1, and that is 0.1, that is x of 0. You see, at t equal to 0, the object is at x equal to 0.1. That's right. So x of 0 is 0.1. At the end of the first second, it is at this x value. Therefore, the distance traveled in that time is 0.029. Now, this is where the object is at t equal to 0, at 0.1 meter. After 1 second, in 1 second, the object moved over here. Its position is 0.071. Therefore, this is the distance traveled in that 1 second, which will be 0.1 meter minus 0.071, which is 0.029 meter. Alright? So x0 minus x1 is 0.029 meter at that meter there. We now need to find the distance traveled in the second second. Now, how do we do that? We know at the end of the first second, the object is here. Let's find out where is the object at the end of the second second. The position at the end of the second second is x of 2. X of 2 equal to 0.1, that's your A, cos pi by 4 t. T equal to 2. Alright, what is the value of that? That is 0. So at the end of the second second, the object has come back to x equal to 0 somewhere here. I think I've got my animations messed up, so it's going to come a little disorderly. The distance traveled in the second second will be x1 minus x2, because it is at this point at the end of the second second. Alright? Then the distance traveled will be this position minus that position. Well, here is it. X of 2 equal to 0. That means the distance traveled during that time. This is the second second. You see? The first second, the object travels from here to here. The second second, it travels from here to here. What is that distance equal to? It will be x of 1 minus x of 2. That will be 0.071 minus 0. That is 0.071 meter. Alright? Next we need to find what is the distance traveled the third second and the fourth second. The position the position. Now you must distinguish between distance traveled in the third second and position at the end of the third second. X of 3 gives you the position at the end of the third second. It will be 0.1 cos pi by 4 t, t is 3. And that gives me negative 0.071. So at the end of the third second, the object is here at negative 0.071. So the distance traveled in the third second is x2 minus x3. Is that right? x2 minus x3, that is 0 minus negative 0.071, and that is 0.071 meter. In the third second, look at the symmetry here one more time. The distance traveled in the first second is 0.029 meter. Distance traveled in the second second is 0.071 meter. Distance traveled in the third second is 0.071 meter. You see, these two distances are the same. Can you tell me what will be the distance traveled in the fourth second? I'm going to leave it for you to figure out. Alright. So, you can see these kind of problems, the visualization is very important. Alright. Now, there is actually one more problem left in the PowerPoint. I'm going to leave it for you to do that on your own, because a similar problem has already been worked out. Okay, well, we have done a number of representative problems from oscillations, and these kind of problems are very typical, and you should be able to do all these kinds of problems. Alright, I'm going to stop this in here. We are going to now go on to the next lesson, that will be applications of oscillations. Simple harmonic oscillations. We will use this to develop the concept of wave motion in the next lesson. I will see you for that lesson a little later.